When a database gets large, it can start to perform poorly. This can manifest in slow query speed. You can speed up a query by defining an index, which is a data structure that allows for faster access to the data that is being indexed. As a consequence, whenever you update that database, you will now need to update the index with that new piece of data. The more you index your data, the faster the access time. In order to have more indexes, you must pay a write penalty in order to maintain consistency around that data, since the indexes need to be updated with each new entry. And this illustrates just one simple trade-off that a developer can make within a database deployment. The question of trade-offs is why there are so many different databases in the world. Obviously, these different databases can mostly fulfill our basic needs of storing and retrieving data. So why do we need SQL databases like Postgres? Why do we need document databases like MongoDB and key value systems like Cassandra and search systems like Elasticsearch? It's because each of these systems are optimized for different sets of trade-offs. And trade-offs can affect the speed of a read, the speed of a write, the user experience, the consistency of data, and the cost of running the database. Learning about these different database features and trade-offs can help you understand how to evaluate which database to choose and how to optimize and assess the performance of a database that you've already deployed to see if maybe you want to tweak it or maybe you need to switch to an entire database altogether. Andrew Davidson is the lead product manager of MongoDB Atlas. Andrew joins the show to talk about how database performance can degrade when a database gets large and how to measure and optimize the performance of a critical database. Andrew explores the range of distributed systems cases, from a single node database to a multi-geographic distribution of nodes around the world. And he describes how the configuration of a database in the cloud can help or hurt the application that the database is serving. Full disclosure, MongoDB, where Andrew works, is a sponsor of Software Engineering Daily. I have learned a ton from QCon. QCon San Francisco takes place this year, November 5th through 9th, 2018, and I will be going for my 4th year in a row. I always love going and seeing the talks, and in between the talks, I hang out and eat some mixed nuts, chat with other engineering leadership about the latest talks and stuff that they're seeing, the 50 different stream processing systems that we're seeing, the different databases we're seeing. And QCon is a place where senior software developers and team leaders and managers and senior leaders, they all gather together and you have fantastic conversations, you have fantastic presentations, and it's extremely high quality. It's technical. A lot of it is also cultural and about management. And you can get $100 off by using the code SED100. QCon is a great learning experience. The presentations this year include 18 editorial tracks with more than 140 speakers from places like Uber, Google, Dropbox, Slack, Twitter. They are curated, high-quality talks, and you can get $100 off if you use code SED100 at checkout for your ticket. Again, QCon San Francisco takes place November 5th through 9th, 2018. And the conference is the 5th through the 7th. November 8th through 9th are the workshops. You can go to QConSF.com to find out more. And thank you to QCon. If you are going to buy a ticket, please use code SED100. And we really appreciate the sponsorship of QCon. Andrew Davidson, you are the lead product manager at MongoDB Atlas. Welcome to Software Engineering Daily.
Thanks so much, Jeff. Great to be here.
I want to talk today about database performance with you. And the first part of the topic that I'd like to explore is why there are different databases, because there must be some different trade-offs between these different databases, but to some degree, they are giving us the same thing. We ask them for data, they give us data back. Why are there so many databases?
Well, that's a great question. I mean, there are so many databases basically because the database and the data are the heart and soul of the application and are so just fundamentally critical to building great application experiences, no matter what we're building today. And I think just as we're sort of seeing this new trend where people are actually starting to build custom semiconductor level hardware for various applications, which is something you have to do if you want to optimize, a new IoT device. You go one layer up in the stack. If you're building an application and it doesn't have the right impedance match to its data store, it can really fundamentally slow down what that application could do. It's not necessarily really all about performance. I think a lot of times folks talk about performance or, benchmarks and such, but really the most important thing is often how, basically when you're building an application and iterating on it, it's a question of, for the developers building that application, can they continue to iterate and achieve their goals at the beginning, the middle, and also at scale or in maintenance mode for years ahead. All of those are critical things that fundamentally are set based on this impedance match between their application and their database. So a lot of folks have gone and built new databases because they had some novel application they were trying to build. In fact, MongoDB came out originally because the founders of MongoDB were trying to build really a platform as a service, and they needed kind of a database to back it. And they eventually realized that the database itself is such a big project and caught on, they should continue with that. And I think that's happened to a lot of folks. I read a fun Hacker News comment from someone once who was basically saying, if a project involves inside of it a database project, then it is just a database project, essentially. So I think it was a riff on someone who said, if a project involves building a space launch vehicle, it's just a space launch vehicle project. In other words, databases are extremely big things. And so folks often will end up building them for custom use cases.
Right. There are different trade-offs that different databases can make, and these trade-offs can exist on the axis of performance, like the speed of a write or the speed of a read, but also on the developer experience or some UI layer that you build to make it easy for people to interface with the database from a web browser, for example. You can also make trade-offs on the axis of cost. What are some of the different trade-offs that a database can make?
Let's just start with the sort of the elephant in the room when we're talking about MongoDB in particular is fundamentally it's this very different data model from our traditional table-based relational databases. In other words, with a relational database, which came out of the 1970s world in which, very different time. At that time, the cost bottleneck really was all about storage. In other words, if you could keep storage costs low, that was of incredible value. You could throw as many people as you wanted at the problem because your storage was the key bottleneck. That was the 70s. And this idea of having a bunch of tables linked with keys and having your objects sort of mapped across them all made a lot of sense when storage was all that mattered to keep down. With MongoDB, what happens is all of a sudden this concept of a particular object in one's developer code, in an application code, being spread across a bunch of tables goes away. Typically, an object, instead of it requiring a join across a bunch of tables, an object is simply described the same way in your Java or your Python code as it would actually be in the database, as a document, similar to JSON in structure. And this uses, of course, obviously it uses more storage because you're denormalizing data across different environments. But of course, today storage is really cheap, and that's not generally the problem. The problem today, the bottleneck today, is developers' time. Basically, the ability to quickly understand what's going on, make changes, change their application, and build new capabilities. And when you don't have to think about these complex joins across lots and lots of tables, you get a lot of benefits from a developer experience perspective. If you look at a lot of code, typically a developer writing code with a relational database will have an object relational map, an ORM layer. And essentially that layer is something, some people love it, some people hate it. In any event, that's kind of the key layer where you get this bizarre impedance mismatch when you're going to a bunch of tables underneath. And that layer effectively gets replaced by the database when you move to MongoDB.
So there's also the ability to move between different databases for different applications. So for example, Mongo is often used as a transactional layer because developers can write their front-end application code against that Mongo database because the structure of the document model is, like you said, reflective of the way that I want to think about my application level services, the way I want to think about my customer facing services. I want to make a write to a user document or a post document. I want to create an order, and I want to think of these things as JSON document models because that's where most of the interaction is. That's how objects are structured on the front end, and so it's how you want objects structured in your transactional layer. But there's also the option to move that data from the transactional layer into other databases in order to perform jobs that are more reflective of certain back-end processes. So, if I'm writing a front-end service, maybe it makes sense for me to be in the paradigm of updating document models, but that doesn't mean that I can't have ETL jobs, these extract, transform, and load jobs that transform that transactional data into a MySQL database or a data lake that's in Parquet files that are column oriented. You can have your operational data map into other data formats in order to write backend applications that might need to grab everything in a column. Could you talk about that in a little more detail? When do people want to do ETL jobs from one data system to another, and why do they need to have these ETL jobs? And why does that relate to database performance?
I think I'll start off by saying nobody wants to do ETL, in that it tends to be one of the sort of the typically the things that folks find are further removed from where their business is, where their customer is, and it's kind of stuff that they wish they didn't have to do, but nevertheless have to do. And they have to do it a lot of the time because they have critical stakeholders, whether it's business analysts or product managers or an executive dashboard who just need to be able to understand what the application data is telling them so that the company or the application team can make better decisions about where to go and track what's going on. So I think they use ETL because the pain point is those stakeholders can't easily learn those things if they don't or traditionally have not been able to. And to your point, yes, they go to data stores that are optimized for queries on a particular field, like a column store. And what that means is sort of on the, at the I/O level, with a column store, you're pulling out from every page from disk, you're essentially pulling out a bunch of values from a bunch of different rows, or in MongoDB nomenclature, a bunch of different values from a bunch of different documents, all together without getting all of the other columns or fields from those same documents or rows, which is what a row store, or which is sort of the MongoDB model, more of a B-tree model. So yeah, columnar storage, going truly offline into object storage, like you said, maybe in Parquet or CSV. These are all things that a lot of folks do so that they can more easily service those other kinds of stakeholders. I will point out that what a lot of folks will do with MongoDB as an alternative to doing ETL is you can use read replicas for workload isolation. And that way you're not impacting the performance of your main cluster, but those replicas are already there for high availability anyway. And you can have sort of offline analytical aggregation type queries against them. You can also do the other key thing is a lot of these business analysts, they might query the data with just a different query language. They might really want to use SQL. SQL is not ideal for developers because it's that impedance mismatch to their applications, but a business analyst worldview where they want to declaratively describe what they want to pull back, a lot of them love SQL. So the ability to kind of ETL into a SQL native data store can be compelling to them. MongoDB does have a BI connector which will convert MongoDB to SQL, but it doesn't have, for example, the columnar performance advantages. So it's a question of, do you optimize for performance from the data store, but then you're having to do all this ETL type work, or do you sort of perhaps optimize for reducing things like the ETL plumbing, but leverage, converters that make different data stores look like other kinds of data stores?
You're saying that in some cases ETL works, but in other cases you may want to do something else.
Yeah, I mean, basically ETL is a cumbersome thing to do. And so you can do ETL if you really want to move into a data store that'll be like the best performance for your data analyst. But if you're willing to have your data analyst use okay performance and not have to use, for example, do all the ETL work, Then you can actually just do things like the MongoDB BI connector, which will speak SQL for an analyst to the database, to MongoDB natively. And you can do that against read replicas, so you have workload isolation, not hammering your production database.
What is the point at which the approach without ETL, or one of the approaches without ETL, so either the read isolated replica or maybe just having the business analyst accessing the operational database because you don't have that much data, or the workload is just not too intensive. But what's the point at where things start to fall over and you do need to do ETL?
I think it all really depends. I mean, every company's different. Like some folks, for example, want to move to HDFS because they already have a big investment in a large Hadoop cluster. Although I think, I'd be curious to hear what you think, Jeff, but over the last few years, I think we're seeing a bit of a shift away from excitement over HDFS and Hadoop towards really it's more about compute at the Spark tier without it being all about HDFS. And you can do things like Spark natively against MongoDB as well, against those read replicas. So I think it really just depends. I mean, if you're trying to do massive scale, machine learning, you don't necessarily want to do that off of your read replicas of your operational data store. But if you're having your data analysts do, the key weekly reporting on the context of your application, then that's something very different and something that certainly you might not care so much about having their queries run a little bit longer than they would if they were in an optimized data store.
Yeah, that's consistent with what I've heard from other people. So there are some cases where you can speed up your queries by doing things like database normalization or indexing. Can you explain what these approaches are? Because I want to get into a discussion of some tactics involving database performance and database optimization. So maybe you could define these terms for us: indexing and database normalization.
Frankly, indexing is really the most important kind of performance 101 aspect of MongoDB to be aware of. So, really what indexing is all about is, out of the gate, a default MongoDB collection will have one particular field that is indexed, _ID it's called. It's kind of like the always there field in MongoDB. What this means is if you're running a query against a MongoDB collection, by default, you're going to have to go through every single document in that collection to figure out whether the results of your query are a hit, unless you're querying on _ID. And if you have to go through every document in the collection in order to provide the results, that's what we call, a collection scan, or traditionally a table scan. That basically is very slow. It doesn't always feel slow when you have a small data size and you kind of can ignore it for a while. But as you get a bigger data set, it's just, essentially you're not using a binary search tree. You're actually going through every item in order. And so the speed will just, scale linearly with the size of the data set. Now, indexes come in where you can actually, in MongoDB, decide to add secondary indexes to any field in the document, and those can also be nested fields, and it can actually be arrays as well. You can index arrays. And you can also create a lot of kind of more advanced indexes. You can do geospatial indexes, full text search indexes. And probably the most important is you can do compound indexes. You can have an index that involves multiple fields, which allows you to do things like a query that will involve multiple fields, like maybe type of clothing and also size. If I indexed on both type of clothing and size, I could very quickly provide all kinds of results for someone for whom I know they're looking at pants, I know what size they're in. So this ability to use these advanced indexes, they allow you to not have to do these table scans where time will grow linearly with data size, and instead essentially have more of a search tree or O-log time dynamic, which essentially feels very snappy to the end user. So indexing is just critical. Now, normalization versus denormalization, this basically is all about, do you store data? So MongoDB is all about denormalization for the most part. You're storing data about an object in the document where that object is stored. So for example, if we're storing a collection about clothing and we've got t-shirts, we're going to describe the colors that the t-shirt has right there on the t-shirt document. So if we have a blue t-shirt that's available in one t-shirt brand, we might also have a blue t-shirt that's available in another t-shirt brand. And that's all just fine. They're just attributes of the t-shirts. The normalized model would be to sort of have a separate table where we describe the potential colors the t-shirt could have, blue, red, etc. And we would actually not store this concept of blue right there in our object, right with our t-shirt, but actually look it up through a join. That kind of going back to the beginning, that made sense where it was so critical that essentially we not store blue in multiple documents because storage was so scarce then. But nowadays, the idea of having to do a join just to find out what t-shirt colors are available for t-shirt, is just cumbersome. So denormalization is kind of the new, way to go for developers where it's easier for them to understand what's going on. Where denormalization gets complex is if you have different kinds of data that are related in different documents, and you need to be able to transactionally update them together. In other words, if I wanted to have, the number of t-shirts available in one collection for a certain t-shirt brand, but also have sort of the another collection, which is the number of like someone's checkout cart, their orders. And if I wanted to have, myself add a t-shirt to my cart and also ensure that no one else could therefore get the t-shirt into their cart and therefore kind of decrement the t-shirt counter, I would have to be doing, changing a value involving multiple documents. And that's something that traditionally was very difficult with MongoDB. MongoDB did not have multi-document ACID transactions for the first, call it, 10 years of its database life. One thing that came with MongoDB 4.0, which was released a few months ago in June, was for the first time with MongoDB multi-document ACID transactions. So that canonical example of the, decrement the t-shirt counter so I can check it out and not have someone else is now something that can be, easily done in one's code.
Accenture is hiring software engineers and architects skilled in modern cloud-native tech. If you're looking for a job, check out open opportunities at accenture.com/cloud-native-careers. That's accenture.com/cloud-native-careers. Working with over 90% of the Fortune 100 companies, Accenture is creating innovative, cutting-edge applications for the cloud. And they are the number one integrator for Amazon Web Services, Microsoft Azure, Google Cloud Platform, and more. Accenture innovators come from diverse backgrounds and cultures, and they work together to solve clients' most challenging problems. Accenture is committed to developing talent, empowering you with leading-edge technology, and providing exceptional support to shape your future and work with a global collective that's shaping the future of technology. Accenture's Technology Academy, established with MIT, is just one example of how they will equip you with the latest tech skills. That's why they've been recognized on Fortune 100's Best Companies to Work For list for 10 consecutive years. Grow your career while continuously learning, creating, and applying new cloud solutions now. Apply for a job at Accenture today by going to accenture.com/cloud-native-careers. That's accenture.com/cloud-native-careers. So let's dive deeper into indexing.
Sure.
My sense is that indexing gives you faster speed in exchange for maintaining an extra data store. So there's a slight trade-off between speed and more storage and just an increase in the complexity of your database because you're adding in this new data structure.
Yeah, actually, it's really the key, you're hitting the nail on the head. The key trade-off with indexes is you start paying a write penalty. MongoDB is a strongly consistent database, meaning if I'm running a query and it's served by an index, the index will always serve a query for the latest view of the data. The index will never store like a view of the data that hasn't yet become updated yet. It's not eventually consistent. As a result, indexes are on the critical path to writes. So if you have, you're hitting the nail on the head. It's not uncommon where you see someone who has 20 fields in their documents and they'll have all 20 fields indexed. And that is something that definitely can be that kind of rookie mistake where you might think that makes sense, but then every time you're doing a write or an update, you're potentially having to not just update one place on disk, but you're effectively updating 20 places on disk. So there's this amplification of the I/O required, which absolutely slows things down.
Why is that? Can't you update the index asynchronously from updating the actual field that you're writing to?
So you could do that, but then what's happening is in order to use the index and provide a consistent result, you have to confirm whether or not the index is indeed the latest view of the data or not. So you're paying that penalty somewhere where you either have to go check with the document's current state to see if the index view is the current state. The alternative is to actually say, it's not uncommon for people to say, I don't need consistency. I'm happy to have a search engine. A lot of folks will use search engines that are fundamentally eventually consistent because you're pushing your data out of your operational data store into a search engine. And a lot of the times folks will say, that's okay. For the most part, I'm fine with that. So it's just a different trade-off. But inside the core operational database, at this time anyway, MongoDB does not offer that eventually consistent indexing model.
So the consistency trade-off here is if there's a field that I write to that has an index defined over it, and as I write to that document, if somebody does a lookup for that same object by that index, and the lookup and that index is not locked, then they might get a read of data that is now stale because my write has not finished. So they're going to read stale. The question is, they're either going to read stale data or they're going to have to wait until both the document itself and the index that tracks all those documents that are associated with that index gets fully updated. So you have a trade-off in consistency versus time there.
Yeah, you're hitting the nail on the head. This is, of course, why if you kind of look way down in the stack, the very bottom of the database stack is typically a storage engine. And this is why storage engines are such a just critical part of what makes the database. If you look back at MongoDB's history, probably for the first, I'm going to call it 5 or even 6 years of MongoDB, the built-in storage engine, which was called mmap v1, it was, probably not the strongest part of the database. And I think nobody would think it was. MongoDB was built with great high availability, distributed systems capabilities, replication, and sharding. But the storage engine in those first few years of MongoDB, fundamentally, a lot of people who tried MongoDB in those days, they ran into all kinds of locking contention issues because it's so critical, especially when we start talking about like what we're talking about here, which is document level writes and ensuring that you're not locking for longer than you need to during the context of the write or the write of the index. MongoDB brought in this new storage engine about 5 years ago called Wired Tiger. It's been the default since 3.2 of MongoDB, a couple major releases back. And basically that, Wired Tiger was built by this team that had kind of legends in the storage engine space, had built some significant storage engine offerings elsewhere before they built this offering. And MongoDB, acquired Wired Tiger, made that the core storage engine of the database. And all of a sudden you get that true document level concurrency, which, I would encourage if anyone's listening today who used MongoDB back in those early days where you ran into those locking issues, really everything we're talking about now, it's all about true concurrency at the document level, which is really what you want. I mean, object level concurrency.
Let's revisit normalization. What are the performance trade-offs of normalization?
Well, with normalization, you're essentially having to look in multiple places to essentially, if you want to know, going back to the t-shirt example, if I quickly want to know everything I need to know about my t-shirt, if I can't just look to one place on disk very quickly, just to pull back my document record, then I have to actually jump to a bunch of other places to get the detail about my t-shirt. And that requires us to do kind of similar to the indexing, but the reverse, where adding lots of indexes will force us to do lots of different writes at the disk level when we're doing a single document write. With normalization, on the read path, we're having to do lots and lots of different reads from lots of different places on disk effectively in order to pull everything together, which is you don't want to, that can be frustrating if an object you want it back as quickly as possible because you care about everything in that object or a subset of the portions of that object that matter to you. Not having to have that spread across a bunch of different contexts is an advantage. It's particularly an advantage, or normalization could be particularly complex in a distributed or sharded cluster where you ideally would not want to have to join, normalized data across, different shards or different nodes, because then you're talking about network hops as well to bring the data together. Now, of course, most of the relational databases don't have kind of a distributed paradigm to them. They're typically, standalone or more application tier sharding with high availability built in. So that often doesn't necessarily come up, but with like scale out databases like MongoDB, where sharding is a first class citizen, you want to think about, whether or not you're having to join across, multiple nodes, or if you can keep things within an object, then everything's faster.
So if I'm working with a database and my database starts to go slow, I'm looking at it, what kinds of introspection can I do to figure out what's going slow, and how can I use these primitives, these speed up primitives like indexing or normalization to make my performance better?
Sure. Well, so a lot of folks who come over from a relational background, and maybe they're using MySQL and they move over to MongoDB, it's not uncommon to bring the schema, modeling ideas from relational to MongoDB, and all of a sudden, where they might have had n tables in MySQL, they might use n collections in MongoDB. And this is like a big red flag to begin with, because what's happening is you're using a database that's really built primarily for denormalized, getting the description of the object together in place and indexing it therein. And instead, you're doing a bunch of joins where you don't have to. And it becomes a bigger no-no when you're talking about a distributed system. So, from first principles, it's really important to think about your schema and basically with MongoDB, describe objects, business entities, as an object in your code and just store that the same way inside your collections. And when you do need to do a join in MongoDB, which is not something that happens, but far less than in relational because it's not on every object view that you have to do the join, there's something called $lookup that lets you do it. So assuming your schema fundamentally reflects what your objects are, and that's so important for MongoDB, then from there, you want to index on really what are the most important queries that you need to deliver great SLAs for. And that's different for everyone. I think it's fair to say that the queries that are happening the most frequently, that are on the critical path to your end user experiences, those are the ones that you probably want to index, and you want to look at what you're querying for and simply index on that subset of fields, make a compound index, for example.
So now I'd like to move into talking about distributed systems.
Sure.
And add another axis of complexity into our discussion. First, explain what a primary and a replica database are and some typical setups for a database that involves a primary and a replica.
Sure. So MongoDB uses a raft-like consensus algorithm, which is pretty much the standard today. And the great thing about this consensus algorithm is essentially what you do is you have at least 3 replicas. That's the idea. And the reason you want 3 is that this allows you to do auto failover. You can't actually do auto failover with just 2, and I'll explain why. If you've got just 2, then essentially, and this kind of goes back to the CAP theorem, consistency, availability, partition tolerance. But basically, if you have just 2 nodes and one's a replica of the other, there's no way for either of the 2 nodes to be certain that it should or should not continue to take writes, because it doesn't know basically if there's a partition between the 2, each one will believe the other's down. So they could either both take writes, which can lead to a consistency quagmire where you have different potential application instances writing to different perceived primaries at the same time. That's a kind of a nightmare scenario because there's all kinds of conflicts that can arise. Or you can have both nodes, both replicas sort of say, I can't see the other one, therefore I can't take writes right now. And then all of a sudden you lose write availability in the event of a partition. The beautiful thing about 3, and the 3 is the standard with MongoDB, like if you have a replica set, which is sort of the simplest cluster in MongoDB, it's always going to be 3. There's options to do more than that, but 3 is kind of the default. Or if you have a sharded cluster, each shard is just a replica set of 3 again. So it's the same availability, but it's just scaled out. The beautiful thing about 3 is if you have a partition, the idea is that you would need actually a partition between all 3 to lose that write availability. And that's very unlikely to happen. The key is that any individual node being down when there's 3, or any individual node that appears to be down when there's 3 to 2 of the 3, the 2 of 3 can continue to form a majority consensus, and amongst the 2 of them, elect a primary where writes will go. And this allows you to basically get the high availability you require today without where the cost is, 1, you need to have 3 data nodes. That's kind of That's a key cost. And two, you need to be, there is this model, as far as the cap theorem goes, essentially you're saying I'm willing to sacrifice availability, meaning if I lose 2 of my 3 nodes, if I lose the majority, then I will stop taking writes. But this model, and it's a MongoDB model, and I think it's kind of the emerging standard, this model says I'd rather be, it's so unlikely that I'll lose a majority. I'd rather optimize for not taking writes when the majority is lost, than instead optimize for taking writes in multiple locations where consistency becomes such a problem. MongoDB has always wanted to optimize for consistency. And with distributed system for availability and modern infrastructure, particularly in the cloud, like MongoDB Atlas, what I am the product manager for, where we can automatically spread the cluster nodes across availability zones, which are essentially distinct data centers on the back end of the cloud providers, or you can even go across cloud regions, so 3 or more cloud regions. The kinds of availability you can get today with 3, and knowing that you'll have to have a majority up, you can get easily 4 nines with that. And as a result, optimizing for consistency makes a lot of sense.
We explored a trade-off of consistency versus performance a little bit earlier when we were talking about the question of indexing.
Sure.
And the fact that when you define an index, the one trade-off that you're making is that the index will have to be updated in a consistent fashion with a write. And if you have a concurrent read, then that read is going to have to wait around. Now, that's a single node example of this consistency question, this performance question. With the introduction of multiple nodes, we have a variety. We have a raft of new questions around consistency and performance that we can explore. Explain why the multi-node setup can affect performance, and what are the different axes of performance improvements that we can explore in the context of multiple nodes?
Sure. So there's really 2 key dimensions when we're talking multi-node distributed MongoDB clusters. There's the replication, where you have the same data on multiple nodes, and that's for high availability and for workload isolation. We talked about at the beginning, where you might want to have certain classes of queries target a read replica so that they don't disrupt the primary where writes are going. But then you also have separately sharding, which is scale out, the ability to say, I'm going to take multiple replica sets and distribute my collection across them. So this allows us to do long-term linear scale out, into really any level of scale. Like if we want to go into multiple terabytes, it makes sense to start sharding, because it's just, you have a lot of concurrency benefits not having to have multiple terabytes on one particular node. Now, so when it comes to consistency, it's a great question. When you're reading from a replica, like we mentioned, you might have your business analysts do, or you might just have, or another example might be, you might have read replicas for like in MongoDB Atlas, we make it easy to define global clusters around the world. And you might want to have a read replica from, your US data in Europe or in Singapore to enable low latency reads from those other parts of the world. There's a consistency trade-off there insofar as you don't want to read from a secondary that may be really behind the primary. Or maybe you're willing to, you just have to be aware of whether or not you need to know that when you're reading from a replica, that data may or may not be the latest data. There are some knobs to consider MongoDB exposes. Like you can do something called read concern majority, which basically states that you're reading something that has gone to a majority of the nodes in the cluster, which guarantees that it'll never be rolled back. And a rollback is what can occur when you have an election, like you lose an availability, you lose a node in your cluster, and that was the primary, and you have to elect a new primary, and that happens before the writes have gone to the majority of the nodes in the cluster. So you can use this read concern majority to know that what you're reading will never be rolled back, but the only way to be absolutely certain that what you're reading is the latest that the primary has would be to read directly to the primary. So various trade-offs to consider.
The question of multi-node in a single data center, or even in a single geographical region with multiple data centers,
sure,
can be different than a question of global consistency, where you might have one data center in the US and one data center in Asia, because there can be significant latency and more questions of consistent network bandwidth between those two data centers
Totally.
or between those two geographic regions. How does the geographical, the global nature of if you want global consistency, or the questions you can explore as to whether or not we need global consistency and the penalties that you get for trying to maintain global consistency, how does the question of global consistency, if we're talking about global in the sense of geographically global, like in multiple continents, how does that affect if we're talking about if some global application where we might need consistency, like if we're building Gmail, we probably need some global consistency.
There's a couple options to consider. I mean, the model we've been talking about so far, where there's essentially a primary. So let's take a step back from the data center. Let's imagine that we kind of describe the cloud regions that we're thinking about deploying into. And let's say we describe a preferred region. This is something you can do in Atlas, MongoDB Atlas, for example. On AWS, Google Cloud, or Azure, you choose your region in Atlas, you choose the size of the cluster, but you can also have it be multi-region. Now, let's say you choose a preferred region, US East, for example. You can have those read replica regions elsewhere, but fundamentally, all of those writes by default are going to go into the US East region. So, yeah, there's two things. It's not just consistency insofar as those read replicas might fall behind the primary. I would argue that actually the bigger problem will probably not really be one of consistency globally, but instead that, frankly, your users who are over there in Singapore or in Europe, their writes, that the latency for their writes are going to be painfully slow because they're having to wait for a round trip all the way to the US and back. So really, write latency is the key. And so therefore, the question is, can you have a cluster that puts the primary, so to speak, associated with the data near to where the end users of that data are, and do that in different parts of the world? And we have something called global clusters in MongoDB Atlas, which use sort of a very opinionated version of MongoDB's zone sharding to do just that. And essentially what you do is you take a global sharded cluster, and you essentially are choosing which subsets of shards will be homed in which parts of the world. So you could have a US shard, a Europe shard, and an Asia shard. And what happens is you can have US users write and read locally to the US shard, European users write and read locally to the Europe shard, and Asia users write and read locally to the Asia shard. So for the users, they get what they want, which is the in-region, consistent, and low latency experience for reads and writes. But then you still have the ability to do global aggregations across all of the data because it's a single cluster. And you can, so what you don't get from what I just described is the ability to have read replicas from each of those zones in the other zone. But you can do that. So in Atlas, you could opt into that. So I could have a read replica from my US data in Europe and in Singapore, a read replica from my Europe data in US and Singapore. And Singapore data can have a read replica in Europe and the US. And when we do this, we can get in-region low latency reads for the global data, with the compromise being that the global data from the other regions will be from a read replica and therefore could be a bit stale. So, all things to consider. And if you wanted to get up-to-date region query from the other regions, you just fundamentally have to do a round trip.
DigitalOcean is a reliable, easy-to-use cloud provider. I've used DigitalOcean for years, whenever I want to get an application off the ground quickly. And I've always loved the focus on user experience, the great documentation, and the simple user interface. More and more people are finding out about DigitalOcean and realizing that DigitalOcean is perfect for their application workloads. This year, DigitalOcean is making that even easier with new node types. A $15 flexible droplet that can mix and match different configurations of CPU and RAM to get the perfect amount of resources for your application. There are also CPU-optimized droplets, perfect for highly active front-end servers or CI/CD workloads. And running on the cloud can get expensive, which is why DigitalOcean makes it easy to choose the right size instance. And the prices on standard instances have gone down too. You can check out all their new deals by going to do.co/sedaily. And as a bonus to our listeners, you will get $100 in credit to use over 60 days. That's a lot of money to experiment with. You can make $100 go pretty far on DigitalOcean. You can use the credit for hosting or infrastructure, and that includes load balancers, object storage. DigitalOcean Spaces is a great new product that provides object storage. And of course, computation. Get your free $100 credit at do.co/sedaily. And thanks to DigitalOcean for being a sponsor. The co-founder of DigitalOcean, Moisey Uretsky, was one of the first people I interviewed, and his interview was really inspirational for me. So I've always thought of DigitalOcean as a pretty inspirational company. So thank you, DigitalOcean. We've now talked about theoretical concerns at the single node level and at the distributed systems level, and the bottlenecks that a developer might have as their database scales up. I want to talk now about product development of building databases, because you work at MongoDB, you lead product management at MongoDB Atlas. So I'd like to talk about MongoDB Atlas as a case study in building a database system that satisfies some of the challenges of the developer that's working on a large-scale database. So what is MongoDB Atlas, and what do you do as the product manager on it?
Yeah, sure. So MongoDB Atlas is an elastic database as a service for MongoDB. It's available on the big three public cloud providers, AWS, Microsoft Azure, and Google Cloud. But MongoDB Atlas is the kind of thing where you sign up on our website. In other words, it's our service, but you choose exactly which cloud region to deploy your cluster into. And then you can connect locally from your application infrastructure in that same region to get in-region latencies. Atlas has all these capabilities, like you can scale your cluster up and down with no downtime. You get all the operational requirements you could ever want, from monitoring and alerting to backups. And you can do a lot of those key workflows, like restoring or cloning a backup from production into a staging environment, so you can test next week's production code against last week's production data. All those kinds of things are easy to do through Atlas, because everything you can do in the UI, you can also do through the API. In other words, it's very much built in the infrastructure as code paradigm to be very developer-centered. But it's all, from a product management perspective, it's very exciting, but it's also fundamentally challenged, because MongoDB Atlas is a general-purpose platform, as MongoDB is. And we think about first-class customer experiences ranging from the solo developer, who may be a student trying a new side project, and we in fact have a free forever, free tier, simple MongoDB cluster with half a gig of storage. Anyone can deploy that, sign up in Atlas, get it today, and never have to worry about paying for it. And that's there to ensure that folks just always can try new ideas on this. It's like an alternative to the laptop, but running it in the cloud. We think about that solo developer who's starting with a new idea or maybe learning about MongoDB for the first time. But we also think a lot about, an application team that's seriously in production. They're thinking about what they need to do to scale, and basically what their journey looks like to have an optimized set of workflows so that they can do as little of the plumbing as possible and focus fundamentally on their application, on their end customers as much as possible. And then we also think about kind of what you might call the more traditional enterprise customer, who will have a lot of the traits of that second category I mentioned, but also will require end-to-end security best practices, be fully auditable, and the compliance capabilities, and really have centralized controls that someone who's more of I'm a smaller startup, I'm not thinking as much about. The bigger enterprise requires a lot more of those capabilities. So we really think about optimizing for all three of those categories. We think all three are just critical to the long term for MongoDB Atlas, because we think that someone who starts in one can very easily grow into the next one. And our goal is to really be a ubiquitous data layer that's easy to access for developers really at any level of adoption.
I think of this category of products as database as a service, and it relates to the platform as a service model. So if you go back to the early days, I guess Mongo even came out of a platform as a service approach, as you mentioned earlier. They were trying to build a platform as a service. They ended up building a database, and now I guess they've kind of come full circle because a database is a service. But so when I think about my first time deploying to AWS, I remember doing this like 5 or 6 years ago when I tried to deploy to AWS, and it was really complicated, and there was just so much to do, and I think the docs were out of date, and it was just difficult. And then I tried Heroku, which is a platform as a service, and Heroku was much easier, and I knew that there was the potential to scale up, and I wasn't going to have bottlenecks, and the only thing is I would perhaps pay a little more than if it was on AWS, but it was going to save me time. And so I have not been shy about talking about how much I enjoy running my applications on Heroku, and I think there's a lot of people out there who like to do that as well because it's a platform as a service that simplifies your life. And there are other platforms as a service. Heroku happened to be the one that I started using early on. But when you think about the mapping from platform as a service to database as a service, so platform as a service solves some scalability problems. It solves some onboarding complexity. What are the parallel problems that a database as a service solves?
Let me just first take a step back and say we actually coach a lot of our customers who are starting on-prem on thinking about what it means to shift to cloud. And the key detail that can so easily be missed is it's not just enough to move to cloud. And obviously, in your case and in my case, a lot of us just started in cloud. But for folks who started on-prem, or for us who started in cloud, it's not just enough to be using cloud to be getting the benefits of what cloud really unlocks. The key benefits that cloud really unlocks, the true return on investment, comes from when you can leverage as a service offerings, frankly, wherever you can. Because it allows you to go focus on your expertise, which is your own business, and not focus on the kind of plumbing and all the end-to-end expertise required to do those various layers of the stack. It's easy to kind of write off the notion of, I'm going to run my own databases internally or run my own MongoDB or any other database. It's easy to kind of feel like, it sounds straightforward. I'll just start some software and be done with it. But it's just not at all that simple. It becomes this giant technical debt. You have to think about infrastructure provisioning at the instance level, VPC level, the network connectivity configurations, security setup, TLS configuration, authentication configuration, operating system patching, database level upgrades and patching. You have to think about just setting up your distributed systems, thinking about ensuring that your applications are connecting to them all. And then you have to think about all of the upkeep of all of that and being able to be ready to do that in an automated manner every time you have anyone new who wants to do anything more with your database or spin up a new environment for your database. All of that becomes just a huge time sink. And it requires a lot of expertise that, frankly, a lot of us don't have. We don't necessarily all know how to ensure we have end-to-end security best practices built in. That's where something like MongoDB Atlas, which just has end-to-end, authentication required, TLS required, firewall required, encryption at rest required, can't shoot yourself in the foot as a result. All of those things are all about saving you time and allowing you to focus on your business. So as a service is just really what it lets cloud really let you see the true benefits of cloud. Unfortunately, a lot of folks will treat cloud like their data center and manage a bunch of infrastructure in it like their data center. And all of a sudden, it's not that different than what you were doing when you were using a co-location space. You're just treating it that way. Now, I will share that you're right, that MongoDB Atlas is sort of more like a platform as a service. In particular, it starts looking more that way with something called MongoDB Stitch, which is actually layered on top of Atlas and is a serverless layer above MongoDB Atlas. So you could run, serverless functions there. You can also run triggers based on changes in the database. And we have something called Stitch Query Anywhere, which allows you to actually run MongoDB native queries directly from your clients, from your JavaScript code. So you can sort of see MongoDB in a way becoming a bit more hybrid with our cloud platform, but we're still by no means a full service platform as a service today.
This is actually something I wasn't planning on exploring, but it's an interesting area that I know people who are listening are curious about. So the migration to serverless infrastructure, or the movement towards serverless infrastructure, some of it is standalone functions as a service that people stand up on Amazon Lambda or Google Cloud Functions, and you just call these things ad hoc to just trigger some function. Other times, there are other serverless platforms, like we've talked to Auth0. Auth0 has a serverless platform that has triggers that you might want to tightly couple to your identity platform. So you start to see, and we've talked to Cloudflare. Cloudflare has another serverless offering that they tightly couple to things that you would want at the edge of a CDN, for example. And here you're saying there are potentially serverless functions that you want to be tightly coupled to your database logic, or perhaps geolocated close to your database. What are some examples of serverless functions that you might want to deploy close to your database? Whether we're talking about close logically, like this is logic that relates to my database, and therefore I want to define some JavaScript function that's close to my database logically, or geographically, if you want to literally deploy it close to the database.
Yeah, I mean, I think there's lots of, sky's really the limit on the permutations of this, because it's really all about saying, I'm going to, with low latency, very close to the database, be able to execute compute of essentially arbitrary functions that I could do. So maybe I want to simply change or kick off a workflow based on a change in the database, or a webhook comes in and I want to turn that into a new kind of object in my database, and I want to kick off an SMS via Twilio service. All of these kinds of, they're all related. Like you mentioned, Auth0. All of these as a service kind of serverless layers, they're all related in that you can start integrating them with each other to basically be able to do all kinds of interesting things that you need to do to build a modern application, whether it's tapping into a quick voice-to-text service, or triggering an SMS or an email, or doing a quick image recognition service, or anything under all of the above. All of the, building a modern application, you want to leverage all these things rather than build each of those things custom yourself. And these serverless layers just allow you to more easily plug into those things without you having to run the boilerplate application code that does all of that interfacing. So it's really all about, again, saving time, but it is a big mental shift.
Are you seeing people making that mental shift and going fully serverless or going in that direction?
The way we, for example, built Stitch above Atlas is all about this idea that you can have any mix of regular old app code running against your database and some set of services using Stitch, or you can go all in on Stitch, and you can do everything in between. In other words, it doesn't hide the database, which, frankly, some of the other serverless platforms are more about hiding the database, like you must use the platform. Our approach is you can use MongoDB as much as you want directly, or you can go up one level and do functions in our serverless layer as well. What this means is a lot of folks are going to start small. They're going to have a pre-existing application, and they need to add a new capability. Maybe it's, I need to add in my image recognition software. I want to upload images, and I want them to quickly get like an estimated, image to text or something, right? You want to add that in. Maybe instead of having to put all the boilerplate into your standard app code, you start just leveraging a Stitch function for some of those capabilities, and then you can, over time, add more capabilities that way. So I think today we're still in most people would do the mix mode rather than all in for most applications.
Yeah. I think the usage of these kinds of things are going to really pick up eventually. I did an interview recently with this real estate AI company, really savvy engineers, and they started their company just in the last couple of years, and it's entirely serverless. And it's one of the first companies I've talked to who they just don't even have the notion of, maybe in some edge cases they're quote running their own infrastructure, and even in that sense they're running it on a cloud provider, they're running it on AWS or running it on Google Cloud, but they have gone all in on managed services and functions as a service, and in return they get such operational speed and high uptime that they can just move faster with a smaller team. And it's really amazing because I did that interview fairly recently. I started hearing about these serverless things, 2-3 years ago, and it just takes a while for it to really percolate.
Totally.
And to make it, get wide adoption, get acceptance. Yeah. And I guess people also still have to figure out, what are the patterns that we're going to be following here?
Exactly. Like knowing how to appropriately set up test staging environments, knowing how to store your code in GitHub the right way for this new paradigm and how to get it in and out of the serverless environment where the functions are running from your repository. All of these kinds of things are just new for people. So yeah, it's definitely exciting to watch. Still early days, but yeah, the times, basically, if you're a technical person, you're very much a scarce resource in your company today. And I think all of us, we find ourselves doing things that feel laborious on occasion and feel like they're kind of not strategic use of our time. It's easy to kind of not think about it at the individual level, but when you look at it the big picture wise, your company wins and loses on essentially making you productive as a developer. Nowadays, developers are the kingmakers. Essentially every kind of company, because every kind of company, digital experiences are make or break for their brand. And so, it's kind of easy to not feel or not notice, kind of like death by a thousand cuts, the cost of something you could be using that you're not yet using. But I think as a developer community, there needs to be kind of a recognition of you actually have a lot of power and things that you demand that make you more productive, like moving to as a service type of offerings. Those capabilities, people are going to listen to what you want because it's vital to the business.
We started by talking about performance and we moved into talking about product development. I don't think we've really bridged those two. So I guess to wrap up, could you talk about a particularly difficult product management or engineering challenge that you encountered while building Atlas?
It's difficult to say there's a specific item. I mean, there's a endless and relentless. We've got call it over 100 developers and product designers working full time on our cloud offering. So this is a big offering. We're constantly iterating on it. Relentless. Every 3 weeks we have a new release with new capabilities. But so I think from a product perspective, that the challenge is knowing how to optimize what should we build that will help the most of those three categories strategically the best, quickest, versus what are things that are nice to haves that we're going to do later. And so I'll give you a good example. I mean, one of the key things that we always knew when we built Atlas is, a canonical MongoDB replica set has 3 nodes, right? And we're going to support in Atlas. We knew from the very beginning we're going to support at least the big 3 public clouds. And we do today support the big 3 public clouds. And so we always kind of knew it would be just so awesome if we could just do MongoDB cluster that spanned all 3 clouds, Amazon, Google Cloud, and Azure, and you could withstand a full cloud outage. And yet, this is the kind of thing where most of our customers are not really ready to take advantage of that because their application infrastructure is not multi-cloud yet. They're all thinking they need to go there eventually. So as a result, we've focused Atlas on building great in-cloud cluster experiences, and we haven't gone multi-cloud yet for a particular cluster. We have live migration so you can move from one cloud to another with essentially no downtime. We have a live migration so you can move from self-managed or on-prem to Atlas with no downtime. But what we haven't done yet is true clusters that span Google, Azure, and Amazon, and AWS. And from a product perspective, it's a great example of it's a big project. We want to get there, but knowing exactly when we'll get there and when we'll be able to finish all of the work required to get there, it's one of those things where you can, if you go too early to do those giant product deliverables, things that most folks aren't yet ready, then you're doing so at the expense of a lot of your current customers who have a lot of other issues that you need to optimize. So that's a tough one that we've made the decision around sort of doing it a bit later and just focusing relentlessly today on all of our existing customers and their needs. But that's still quite a myriad set of needs you can imagine.
Very interesting. Yeah, and thinking about it from a strategic perspective of, Mongo has a very successful business and then they decided we're going to create a cloud offering. I think it makes a lot of sense because it's doubling down on the core competencies of the company and really focusing, like the fact that there's 100 people working on this cloud offering. That's a serious dedication of resources to building a cloud service, and it sounds like there are enough challenges to accommodate those 100 people.
Absolutely. And from a sort of a big picture perspective, not just looking at cloud, MongoDB, we think other than the fundamental data model being what developers from an impedance between the app and their data need today, it's all about agility and what they want today. Other than the data model, and other than just the core benefits of the distributed system, which gets you all the things we talked about earlier, really the other key value proposition of MongoDB, generally speaking, is that you can run it anywhere. You can run it on your laptop. You can run it even on the mainframe, if you can believe it. You can run it in your data center. But of course, we built Atlas so that if you're running it in the public cloud, you could get a more exceptional than ever experience, true as a service. But it's still the same database no matter where you run it. You're never locked into a particular cloud. You're never locked into Atlas. You can always go, make those changes. And we think that that's really about liberating our end users so that they feel that MongoDB is really a liberating technology. And I think that has some nice alignment to what's been happening around application portability with a lot of the, like the trend towards Kubernetes and other platform as a service thinking at the app tier, which is basically allowing it to be easier than ever to move application infrastructure around, stateless infrastructure. We think that those are a great combination. You can easily move your apps around, and you can now easily move your database around with MongoDB having a consistent experience everywhere. So we think running everywhere is very valuable to people. Maybe not immediate value to a lot of folks, but a strategic long-term boardroom level, we think that's very valuable.
Okay, Andrew. Well, it's been really great talking to you, and I look forward to seeing the developments in the future for MongoDB.
Jeff, thank you so much, and really great. Thanks for having me on.
Failure is unpredictable. You don't know when your system will break, but you know it will happen. Gremlin prepares for these outages. Gremlin provides resilience as a service using chaos engineering techniques pioneered at Netflix and Amazon. Prepare your team for disaster by proactively testing failure scenarios. Max out CPU, black hole or slow down network traffic to a dependency, terminate processes and hosts. Each of these shows how your system reacts, allowing you to harden things before a production incident. Check out Gremlin and get a free demo by going to gremlin.com/sedaily. That's gremlin.com/sedaily to get your free demo of how Gremlin can help you prepare with resilience as a service.
Wow.